This is the final day of notes for Chapter 20 from the McGraw-Hill book, and it's to finish up electrochemistry. So kind of just tying some loose ends together here, things that we may have already talked about, but I wanted to make sure that we put them down in print. When we add cells together, we get a battery. So a battery is a series of cells. We connect them in series, kind of head to toe, plus or minus, plus or minus. We connect those all in series, and we add the voltages, and that gives the total voltage that we get in a battery. So if we don't have enough voltage to drive something, we could put several cells in a series, and that would give us a higher voltage. We could keep adding those as long as as we needed. One of the examples, the Tesla, which is a really cool electric car, actually had AA batteries. I think they said 10,000. I sometimes wonder about that, but that I actually saw a large case that had AA batteries inside that were connected in series, and it added up to give you the voltage to drive the car. And it drove very well, too. So, two general types of electricity that we use day in, day out is AC and DC. The current in our house, our plugs, our lights, current here in the classroom, that's AC current. AC means alternating current. AC means it goes from a positive voltage to zero to a negative to a zero to a positive. It's kind of like a sine wave if you graph the voltage versus time. So the long and the short of that is that kind of like ocean waves, where it goes forward and then back, and then forward and then back, as opposed to DC, which is what batteries produce, the type of electricity, is a constant voltage across time, and that is more like a river flowing. It's continual, the direction's the same. As far as conversion, I know you call it black box or the charger or power supply, but the real name for that converts from AC to DC is an inverter. So an electrical engineer might call it a rectifier. It actually uses diodes, which are one-way valves, and it lets the electricity only go one way. So the forward wave would go through and the back wouldn't. So we end up with the forward wave, and it's just forward and then kind of a blank because there's nothing, because it wouldn't let the negative wave through, and then forward and forward and forward. And then they basically take that the downside of the wave and invert that and only allow that back type of wave to go. Then they add the two back together again. You end up with forward, 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 forward. And they have circuitry to smooth that out, which gives you the DC. And that's how the inverter actually changes, rectifier changes the voltage from AC to DC. Transformer, actually, the way it works, it changes from, say, 120 volts down to 12 volts. The way that would happen is that we would have, like, let's just use this example of 10 wraps of wire on one side of the transformer and 2 on the other. Well, that would be 5 times the reduction, so it would take something that's, say, 50 volts and reduce it down to 10 volts. If we had 10 wraps in one, that would be 10 times, so you could reduce 120 volts down to 12 volts. So using that technique, a transformer can convert from one voltage to another. Most of your devices that use the USB are around 5 volts, so they convert from 120 volts to 5 volts using differences in the number of coils. Generator, that's a device that turns mechanical energy into electric energy. It can be a crank. It can be gas-driven generator. Got basically a generator in your car. They call it an alternator, and it acts a little different than the old generators used to. And power plant, hydroelectric power plant, those are generators. Windmills, those have generators. They convert mechanical to electrical energy. So finally, we're going to end up with spontaneity of redox reactions. So you'll be given a redox reaction. This is actually one from your review, where we have barium 2+ aqueous plus 10 solid. produce barium solid plus tin 2 plus. So basically we've got an oxidation and reduction hidden there, and first step we need to do is separate them. So we're going to write two reactions. We're going to need two arrows. So that's the first step here, is we draw two arrows. On the first one, we're going to do anything that deals with barium, which would be Ba2 plus, aqueous, and that's it. There's nothing else on the left that deals with barium, and then Ba solid on the other side. We put the tin over here, Sn and Sn2 plus. Now we know that barium, the atom or the element, is 0, neutral, and tin is neutral, but we don't have our charges balanced here. So how do we balance the Ba2 plus? Well, everything we're dealing with in this chapter is electrons, so we put 2e minus there and plus 2e minus there. That gives us balanced neutral charges on both sides, and now we can identify what is it they're saying is oxidized and reduced. Well, obviously this is reduced because the E's are being added, gain electrons reduced, so we'll call that reduction. And this one is losing electrons. They're on the right. Being on the right means they're losing, and that's oxidized. They say barium is reduced, tin is oxidized. Well, to figure that out, let's go look at our reduction potential chart. You look at it, and, you know, barium is up there near the top, and tin's down near the bottom. So barium should be oxidized. In other words, they're not right. Not being right means that this is not spontaneous. So we'll say not spontaneous reaction. Now, I may also ask you for the amount of volts produced by the cell, or what is the cell potential, because we're actually not producing volts with this cell. So cell potential would be the E of the cell is equal to the E of the reduced, and they say barium's reduced, so we're just going to call this barium, minus the E of the tin. So when we look up barium, we see that that's like minus 2.90 volts. So it's minus 2.90 minus a 0.14 volts, and we end up with like 2.76 volts negative. Well, negative volts means it's not going to happen. So that is also telling us minus 2.76 volts. And you might want to look up those values. I'm just kind of operating from memory on that. But if those aren't the right values, then you basically plug in the numbers of barium and tin. Barium number minus 10, going to be a negative, I can tell you for sure, and that means not spontaneous. So that's the cell potential, and when cell potential is negative, it's not spontaneous. That you should also be able, if I give you the half reactions, you should be able to write the overall reaction. How would you do that? Well, first of all, make sure that we're balanced. We've got two E's here and two E's here, so we're balanced. We don't have to multiply anything. If this were 2E and that was 1, we'd have to put 2, 2, and double that to 2 so that everything were balanced. So, but we're balanced here. Then you take everything on the right, or on the left, I'm sorry, and put it on the left of the big reaction and everything on the right of the big reaction. And of course the two E's, they're on both sides, they cancel. There you go. We went backwards and went back to the original equation. So if I gave you half reactions, you should be able to write the overall reaction. That is some final notes, and work on your review, have fun in the labs, and good luck.